So first of all, what's a bit? A bit is a kind of a term, not for a particular system, but for a kind of system, a system that has two distinct states that we could label 0, 1, or yes or no, or on or off for something. The whole idea of information is that we can think of all of those different kinds of systems in the same way. Those systems are isomorphic is the term. That gives you kind of a very powerful way of thinking about information in a way that is not dependent on the information being represented this way or that way or the other. So a qubit is the same sort of thing, but for quantum information. So it's a kind of a generic term for systems that have two distinguishable states, but also superpositions. Also, they might be entangled with each other. They might be the spin of a particle. They might be a photon polarization. They might be the current state of a superconducting circuit. I can't even think of all the ways. Two-level atoms.
Right, sure. So the qubit, yes, could be an object like that, but it also, and primarily is, I think, a unit of quantum information.
Right.
So you could say this thing, contains so many qubits of information, or this communication, this quantum communication conveys so many qubits of quantum information. Very different from classical information.
Right. For one thing, as Bill is one of the people who showed, you can't copy quantum information. When I send you an email, I get to keep a copy. But quantum information is not that kind of thing. If I send it to you, I have to give it up. Okay, and so a qubit is somehow more tangible even than a bit. A qubit is kind of a building block. If you want to make a quantum computer, let's say, and lots of people seem to want to do that, then the first thing you have to say is, what are the sort of fundamental units for storing quantum information, to storing a complex quantum state? And the building blocks, very plausibly, are qubits. Those are the simplest possible building blocks, and they'll have to have certain physical qualities. They'll have to be pretty stable, a little resistant to leaking their quantum information into the environment. You have to be able to control them. At least some of them you're going to have to be able to measure. Once again, it's this duality of the word. It's a thing, you can point, there are the qubits in my machine, but also it's a more abstract concept that's about the isomorphism between systems and about a measure of how much information they contain.
Right. You could hold 1,000 qubits of quantum information in a quantum computer that consists of 1,000 qubits.
We were thinking a lot about bits. We were thinking a lot about regular information and how it related to quantum mechanics. Actually, I got hooked on this by Bill. And we were thinking about different problems, and they were too hard.
Yes, that's right. And I remember, and Ben said, maybe we're thinking about it the wrong way. Maybe we need to think about a completely different sort of problem.
Right? Yeah, because maybe we're thinking of the wrong problem. If you can't solve the problem, maybe it's the wrong problem you should be thinking about.
Right.
So instead of thinking about regular, ordinary information, maybe we should think about special quantum information. And then we thought it was hilarious to think that we could measure it in qubits, because a qubit with a C is the distance from your elbow to your fingertip. And in the Bible, the ark is so many cubits long and so many cubits wide. And we thought it would be really, really funny to measure something in qubits. That was the joke. That was the joke.
This came up when you were driving me back to the Columbus airport.
The Columbus airport, that's right.
Right. I had been visiting Ben at Kenyon College, and yes, this on the drive back, and we both got a big kick out of it because it was so funny to have qubit as a unit of quantum information.
Yeah,
and we decided then and there that it should be spelled Qubit to make it as close as possible to the biblical qubit.
Because of course with CUBIT, that would be classical.
Right.
Yeah,
That's right.
And then I dropped Bill off at the airport and drove back. It's about an hour's drive, and got to thinking that actually this wasn't a bad idea, because you could imagine this concept playing a role analogous to the concept of a bit, ordinary information theory. So people had talked about, well, suppose you have a photon polarization, or suppose you have a spin, or suppose you have a couple of spins that are, they would always have to talk about things in a sort of a specific physical implementation. But it was clear they were talking about something more general. And if you had this duality between a qubit as a thing and a qubit as a measure quantum information, that immediately suggested that there might be a relation, that the measure of quantum information might tell you how many of the things you need to do a particular job. And that was the idea that came out of it. So it wasn't just a word.
Right. And I think of this as a key moment in the transition between what I think of as the old quantum information theory
Mm-hmm.
and the new quantum information theory. The old quantum information theory is a theory in which you're trying to convey classical information using quantum signals, quantum objects. But this is different. Now we're thinking about information that itself is quantum.
And that opens up a lot of questions, which is for theorists.
Which is good.
The questions are valuable, but also a lot of possible things, possible ways of going about even familiar tasks. To think, well, the most efficient way to do this might be using some quantum entanglement, or using some qubits or something like that. So in the conference that we've had this week, a couple of people said that you really don't want to think about the qubit as somehow being both 0 and 1. It's really in a special state which is related to 0 and 1 by this combination, this superposition principle. It can also have entanglement with other systems. So some of the ways of talking about what makes a qubit different, it's not very precise. But then again, our language was not really developed in order to talk about quantum physics. So we have to make up new language and be very careful about it.